look at my kind of hit list and we'll go through them in order. So the first thing I'm going to talk to you today about is about the shape of your data. And we have two major terms. Well, I guess there's a fourth one, but there are three major terms. Your data can be symmetric, it can be skewed to the left, and it could be skewed to the right. And I guess the fourth option is none of the above, right? But I'm not sure that's really an option. So I want you to imagine you've collected your data and you've made it into histograms, right? So you've got a good picture. If your data looks like that, right? It's nice and balanced. It can also look like that. It could look like that, right? But what makes all of these shapes kind of similar is that if you take, say, a pen down the middle, do you see that they're equally balanced? They're reflections of each other in the jargon of math. And these are all called symmetric. And when you have symmetric data, oh, evidently I was wrong, we'll get 3 more people coming. When you have symmetric data, there is a relationship between the mean, the mode, and the median. And really it's between the excuse me, it's between the mean and the median. What you can do here is that when you have symmetric data, if you calculate the mean, we'll call it X bar, right? And if you calculate the median, when it's symmetric data, they end up being the same number. So this is symmetric in shape. And the mean and the median end up being the same number. That means that you could get a question where they give you a picture and say, is this symmetric or not? Or they could just say, we've collected some data, the mean was 45 and the median was 45. Is there anything you could say about that data? And you should be able to say, yeah, it's probably going to be symmetric in shape. And we don't need perfection in statistics. It can be a little bit, you know, a little bit more, a little bit bumpier, a little up and downy kind of thing. But the overall basic shape is symmetric. Do you feel you know what symmetric data looks like? Right. It's got a nice symmetry down the middle. Okay. Excuse me. That's number one. Number two is called skewed, strange name, skewed to the left. And that's what skewed to the left looks like. It typically has one hill, although it can have more than one hill. But what's the main feature? The main feature is that this side here is a lot longer than this side here. And this actually is called the tail. So if you have got distribution and it's got a tail, in other words, one side travels on a lot further and the other side kind of just finishes abruptly, right? As we have here. Then this is skewed and you get your name left from where the tail is. So this is skewed to the left because the tail of the data is on the left-hand side. So skewed to the left, that is going on. So that's its name.
I have a question.
Yes.
So on the top, when we have like the hill and then kind of like the camel and then like, I guess, I don't know, a rolling ramp, is the medium always in the middle? Like you drew the median in the first one, but not the second two?
No.
Okay.
Every
That's what I thought. I was just making sure. Thank you.
No, I think it's worth it if I just write them down for clarity as well. So basically, if you have any, there's lots of symmetric shapes, right? There's lots of shapes, data shapes that are symmetric, but there are not that many data shapes for skewed to the left, right? It's basically a big long tail to the left. I guess you could have a couple of bumps here if you like, it doesn't matter. It's still skewed to the left, but there's pretty much really only one shape. Now, when you are skewed to the left, as we are here, the mean is going to be bigger than the median. Now, if you calculated the mean in this data, I don't know, the mean might be here, and the median would be here. Oops, I'm using the wrong words here, sorry. The mean is to the left of the median. That's what I was trying to say, but I phrased it mathematically, and that was bad math. It's better to phrase it that way. If I wanted to write it as math, it would actually be, that's what I should have written. But I think in English, it's better to think of it like this. So if the mean, the number for the mean, right, is to the left of what the number for the median is, you know it's skewed to the left. Now, if you see the picture, I think you can just tell it's skewed to the left. But give you an example. If I said that I had some data and the mean was 12, but the median was 20, I could make an assumption that this data is probably going to be skewed to the left. And the reason I know that is, can you see that's 12 and that's 20? That's going to be more to the left than this.
Excuse me, Professor.
Yes.
Can you make a larger your zoom in, because I cannot see anything what you are writing down, please.
Wow. Can I do that?
Yes.
Should be able to do that. Just hold on a minute. I'm going to have to dismantle my gizmos because it's on a stick. What am I going to do with this stick? No, I'm going to take the stick off. I took the wrong stick off. And I'll do this. Up a little bit.
Yeah.
No,
Larger, thank you.
yeah. Oops, I didn't mean that. I'm bending too much. I'm trying to get a compromise between how much paper you can see and how much I can write. Does that help?
Yes, it helps a lot. Thank you very much.
Okay. Are you using a phone? Is that one of the reasons this is happening?
No, I'm looking right at my computer.
Oh. Okay, it's what it is. Have the lot of you had the same issue? You've just been too polite to talk to me about it. Farah, you had the same issue? So that's why I see these squinty eye faces trying to read things.
Normally it's not. I don't know. It was weird today. It was just a little bit too far, so I couldn't quite catch it.
Yeah.
It might be the color too. I don't know if that color specifically is not helping you.
Okay, it would be better for me if I could go back to the first one. I'll just try and maybe write bigger and keep away from the green. Otherwise, you're going to have the next problem is going to be, I'll be moving pieces of paper around a lot because I'm writing so much, but you can only see a little bit of what I'm writing at any given moment. So let me try this and tell me if it works. If it doesn't work, that's fine. I'll go back to what I just did. So we got this guy. I'll try and bend this back a little bit. Now, that green isn't working well, so I'm going to do number 3, and I'll see if I can do a compromise on this one. I'll try and write a bit bigger, and I'll keep it to black. This would be an example of some data, right? This fella here, and this has a tail. Do you see the tail over here? Make it even more obvious. Nadia, can you see that picture? Or is
Yes,
it...
I can see. Thank you. My
Okay,
yeah,
I'm just keeping away from this red stuff, I think. It's not good, evidently, for some of your cameras. So, in this shape, right, this one here, It's called skewed to the right. And when data is skewed to the right, do you notice that the tail is on the right-hand side? Right, so it takes a while to tail off, but it stops abruptly on that side. And when you have data that's skewed to the right, if you calculate the mean, it's probably going to be about here. And you calculate the median, it's going to be about here. Do you see that the mean is always closer to the tail, right? So I basically look at where the mean is, and that helps me decide if it's left, right, or symmetric. So X bar is to the right of the median. X bar is greater than the median. So if I've given some data and I'm told that the median was 100, sorry, the mean was 100 and the median was 90, I could make the prediction that based on this, it's probably going to be right skewed to the right. Are we comfortable with the three basic shapes and their names? Technically, the fourth one is it's none of the above, right? So I guess you would write none if that happened. So what I'm going to do now, hopefully, is we're going to show you some pictures, some data, and we'll look at skewedness. And when you look at this data, this is like real data, because you know these are very stylized and very nice and curved, but in reality, data zooms up and down a lot. So when you look at these pictures, try and look at where the mean and the median are, because they're really going to be the key to doing this question. And I'm going to rub out the answers because I've got the damn answers and they're distracting the heck out of me. Right, go away. Okay, we're good. I'll be.
So these are for questions like 10, right? Where we're looking
exactly.
at.
That's exactly.
It always helps me to kind of mark what problems they are, because then that way I can make more better. Geez, bad English. I can add to my notes.
Where to look?
I get it later.
Gotcha. Okay, so what I'm going to do is I'm going to show you questions 10, I think it's 10 to 12 or 10 to 13 that do this type of question. And you'll find that they're a little bit less prettier than mine, for want of a better answer. Right, if you look at this data, do you see that the mean is to the left of the median? I know it's very messy because I've got colors and lines, but the mean is here and the median is here. Because of that relationship with the numbers, it's skewed to the left. Now, you might not be able to see the skewedness because the data is going up and down like a yo-yo. I gave you kind of stylized version. This is what real data looks like. If you have a mean and that mean is to the left of the median, then you are looking at skew to the left. You might say, what about the mode? Don't care what the mode does. It has no effect on the basic shape. Now, let's look at this one. The mean is the red guy and the median is that green guy. When you look at this data, what would be your choice? Skewed left, right, or symmetric? The mean is 3.4 and the median is 3.
Would it be?
Come on, keep going.
To the left?
Okay, if the, right.
Because you said if the
right, let me go back
straight,
to the picture thing and we'll see if I can make it a bit clear.
So the median.
If they're both equal, it's symmetric. That's the easy one. We
okay.
haven't seen that yet.
Mm-hmm.
If the mean is to the left, by that I mean the mean is here, right? It's to the left of the two, skewed left. And if the mean is to the right, Skewed right.
Right.
Okay.
Oh, I
so
thought it meant like less than. Is that less than or greater than, or is that arrow?
this here is a greater than symbol. This is a less than. Maybe you shouldn't be, if that's the thing that's distracting you, maybe you should just do it by visually looking at the
Okay,
places.
that's what I was looking at. Sorry.
That might actually make it a little bit easier. But
I
I've
was
given
just
you.
saying, I did a line and then I made an arrow one way and made a note that if the median is here, then I'm identifying where it is. That might be an easy way for someone to make notes too.
Right. You figure
Yeah.
out how to kind of process what I've said and make sense of it in your mind. That means pretty much what you said. So when you look at this question here, can you see the mean is to the right
On the
of
right.
the median?
Yes.
So that's skewed to
To
the
the
right.
right.
Now, here we have a mean. The mode is a total distraction. I wish it wasn't even there. But here is the mean and here is the median. Now, based on those positions, what's this data got?
Symmetric.
It should be if it's pointing at the same guy. Correct. Agreed? They're both in the middle. Well, actually, that
Does
one
it
you
mean-
could do.
What
That
does it
one's
mean
the
when it's-
easy one.
What does it mean when it's asking this? Is it a normal distribution or a
Oh,
not normal
I
distribution?
haven't even talked about that yet. But I
I'm
will.
like,
Okay, what about this one?
That's good to the right.
Good. We're getting them now. Oh, that's the end of this. Okay, so if I gave you a picture, probably it'd be better just to tell you the mean and the median. Would you agree it's easier to tell when you only know the numbers? Because sometimes the pictures are not as clear. Well, the symmetric one was pretty clear, but the others weren't. Use the value for the mean and median, and that should probably make your life easy. So now I'm going to introduce a fella called the normal distribution. Now, if you're going to be a normal distribution, you basically have to have this shape. So are you symmetric? And do you only have one bump? Right? So you're not allowed to be just any symmetric, right? You can't be the camel, right? You gotta be a single hill. If you have a shape that is made up of data that has this shape to it, we call that a normal distribution. It's a kind of a special version of symmetric. Would you agree, out of these three symmetric, only this one counts as a normal? Right? These two are still symmetric, but this one is symmetric and it's normal, right? Are we cool with that? Right, so I'm now going to nip back to those pictures that we've already done the skewedness thing. And, well, I will if I get this thing to behave itself. And we'll see if any of them are going to be counted as normal. Does that look normal to you?
No.
Okay, that sounds it. Does this one look normal to you?
No.
Does this look normal?
Yeah, it looks symmetric.
It definitely is symmetric, but does it have the one hill thing? Is that a camel? I'm making up names. Is that a camel or a hill? You agree it's a camel, right? And camels aren't normal. That's definitely not normal.
how
Oh,
often do you actually end up with normal distribution in data, though?
according to these questions, you never see it, right? But in real life, it's actually quite common. A lot of things that you collect in data are normal in shape. If I collect a whole load of people's heights, weights, ages, how much money they make, the speed of cars on a motorway, right? Those very often tend to be very normal in shape, right? The big chunk of people are in the middle, and some people go really slow and some people go far too fast. It's got that kind of shape to it, right? And when you have height, most people are kind of the middle height, and some really tall basketball players and some really small something else players, right? And so that data is pretty common even although the homework questions made it seem like it never happens, right? So are we comfortable with the fact that some distributions could be normal, right? So that's taking care of that little chunk, I hope. And now we're moving on to a new fella, because I said there's a lot in this. And we're going to look at how to calculate a thing called the Z-score from data.
We're still looking at the homework screen.
Oh, thank you for telling me. So how do you calculate Z-scores from data? That's where we are now. Well, before I get into it in too much detail, let me tell you why you would even want to do this thing called the Z-score. It's actually got a fancier name. It's called the standardized Z-score, but nobody uses that name. They just call it Z-score. So I'll give you a little story to show you why you might want to calculate that. I have a sister, Mary, and I have a brother, David. I have lots of family, but there's two of them. And I'm making this story up, but my sister, Mary, she took an English exam and she got 75 in the exam, right? 75%. And David, he took a math exam and he got 70. And they were arguing about who did better. And Mary went and said, I got more than you. 75 is bigger than 70. I did better. Now, for most lay people, right, people who don't understand statistics, that's a very fair argument, isn't it? You get 75, you get 70. 75 is bigger than 70. 75, she did better. But that's not the whole story. Can't you have a really hard exam and a really easy exam? So how do you figure out how to distinguish between them? Let's suppose that in the English exam, the mean was 60 and that the standard deviation was 10. And David, in his class, the mean was 50 and the standard deviation was 5. So the mean is the typical person in the class, and the standard deviation kind of measures how spread out the data is.
Triana, please stop.
So what we are going to do here is see if there's a fairer way of comparing those two scores, because that's what Z-scores are. They're a fairer way to compare two different things. And I've lost where I was. Oh, where the heck am I? I was doing something there. Are you looking here? Yes, we are. Right. So here's Mary's stuff. This is David. Now, we've got a better picture. We now know what the averaging exam was like. Well, would you agree that the average in the math exam was quite low? So that was a hard test to get any kind of score in, right? And this was a little bit better, right? So that's a little bit easier to get 70, right? Or 75. So this formula for the Z-score is the data, take away the mean, and then you divide it by the standard deviation. So let's find out what the Z-score of Mary is. Well, her Z-score is what she got, her data, 75, take away the mean of the class and divide it all by 10. So that's 15 divided by 10. She gets a standardized Z-score of 1.5. Let's see what David did. Well, David, he's going to have his Z-score calculated the same way. It's the data. His data was 70. take away his mean, which is 50, divided by 5. In this case, you get 20 divided by 5, and you get a 4. So if you want to compare these two, the z-scores are the ones that you use because they're a fairer way of taking into account how hard an exam was and how spread out the scores were in each exam. And David got a 4. A 4 is much harder to get than a 1.5. Bigger z-scores are harder to get than small z-scores. And that means that David actually did better than Mary. And that would be the answer that we would give to which one of those two was actually successful. Now, you can use that same idea if you had two classes at university taking the same thing. So here is two twin brothers, right? I'll call them A and B because I have no imagination for names now. And they both took a stats exam. And brother A got 75 again. And brother B, he got 85. And he argued, look, we both took a stats exam. I got 85, you got 75. I'm better at stats than you are. Well, if it was the exact same questions, right? The exact same physical piece of exam paper, that would be true, wouldn't it? Doesn't matter if you're in two different classes. If you got the same exam, right? Higher score wins. But it wasn't quite the same exam. This exam here, the mean was 40. And the standard deviation was 20. And in this exam, the mean was 50. And the standard deviation was 30. Now, you might look at this data and say to yourself, I'm not sure now which one of those two actually did better than the other. Because obviously 75 is less than 85, but didn't he do it in a test where the average was less? Right? So that's in his favor. The standard deviation is quite big, but in this class, the standard deviation is huge. And that has an effect on how hard or easy it is to get a particular score. So let's figure out, oh, any bets? Do you think it's a draw? Do you think it's brother A or brother B? Anybody got a gut feeling? Brother A or brother B, or it's a draw? They're both the same.
I think they're the same. I could be wrong.
Yeah, you could be. I could be wrong as well because I don't know yet because I made up the numbers but not the answer. So I'm going to find out like you. Yeah, they could well be the same. Let's find out what they are. And this is A. Let's do his z-score first then. Data, take away the mean, divided by the standard deviation. That's 35 divided by 20, I believe. So that's 1.75. That's quite a good z-score. You know, anything bigger than 0 means you did better than average. Right? If we look at brother B then, let's see what his z-score is.
116 his score.
So 85, take away 50 over 30. And that gets you what? 35 over 30? And that ends up being 1.17 roughly. So in fact, in this particular question, brother A did do better. A couple of general things about z-scores. Suppose you get a z-score of 0, because normally we just write z rather than the word z-score. If you get a z-score of 0, doesn't that mean that you got the same as the mean? Can you see why that would be the case? If you got the same score in the test as the mean score of the class, wouldn't your z-score be 0? Because your number, take away the mean, would have to be 0. If you get a z-score that is bigger than 0, then that means you did better than the mean. And it is possible to get a negative z-score. Do you know you could get a z-score of -2, for instance? That would mean you did really bad in the test, because if your z-score is less than 0, you got less than the mean in the class. And the last general point about z-scores, most z-scores are between -3 and 3. We found that out just by we've done it enough times and we've calculated z-scores enough times, and we've discovered that z-scores tend to be between -3 and 3. So see if you do a calculation and you think the z-score is 27 or -40, have another look, because maybe you hit the wrong button in your calculator, right? Vast majority. In fact, we even have a percentage, not that you need to know this, that 99.7% of all data has a z-score between -3 and 3. So you would have to be like the best person in Washington State to have a z-score that would be bigger than 3. You know, that kind of rarity, right? So it happens, of course, but 99.7% of the time, people have a z-score in that range. Sometimes what they do is they use z-scores to decide what is exceptionally unusual. We call those things outliers. If you do enough statistics, you'll learn about it. Bill Gates, for instance, would be an outlier if you were talking about wealth. And the fact he's getting divorced and now splitting in two, he's still an outlier, because the money he's making, half of what he's got, still makes him phenomenally rich, right? On the other extreme, some of you may be an outlier on the negative z-score. You might have a lot of debt because you're a student and all that carry on, unfortunately. Are we comfortable about how to calculate a z-score and how you could use it to compare two different groups? Back to this one. See if you were at a university and they had more than one stats class and it was taught by a different professor especially. They may well standardize your scores.
Could you do an example of the homework? Because when they do the homework question, they don't actually ask for the z-score. They give you the z-score and they want you to find the data.
Yeah, we have that to do. Well, actually, yeah, you're right, they do. Which brings us to C. How to calculate data from the z-score, right? Okay, so suppose I gave you the mean and I said it was 50. And I told you that the standard deviation was 10. And I told you that the z-score was, I don't know, 3.1, right? So we'll make an exception, right? Somebody with a really, really big z-score. We would like to get the original data, right? What would that person have got in the test, right? To get that kind of z-score. And there's a formula for it. And the formula is the data, the guy you're looking for, it's equal to the mean plus the z-score times the standard deviation. So here is the formula that you will use to calculate the data. I must have forgotten the homework to put one the other way around, but that's fine. You've seen how to do it. Right. Well, let's put this one into practice. What did the person get in the test? What's his data? Well, the mean was 50. The z-score was 3.1 times 10. So that would be 50 plus 31 So that person would have got 81 in the test. It's really just a plug and chug, isn't it, in both cases? If you want to find the Z-score, don't you just use this formula and plug in the numbers and you get the answer? And if you want to find the data, you have this different formula, you plug in the numbers and you get your answer. Is that good? Now, I forgot to mention, because it's so obvious, I just forget things sometimes, that these Z-scores and these calculations that we've been using make one very big assumption, that the data is normal. If it's camel shaped or weird shapes, skewed left, skewed right, anything like that, you could do these calculations, but they have no real meaning, right? They don't make sense in the real world. So Z-scores are only and should only be used when you're pretty comfortable that the data is normal in shape. And it doesn't need to be perfect. Close enough will do, right? So if it's mostly a hill, it's got a funny bump or two, ain't a big deal, ain't a big deal. So let me pick one here. This is a version of the homework question 14. The mean in this case is 85.7, and the standard deviation is 4.86, and the Z-score is negative 3.46, and we're going to find the data. So it's going to be the mean plus the Z-score times the standard deviation. In this question then, it's going to be 85.7 plus negative 3.46 times 4.86. Now you're going to do this, guy, you probably should do it in the calculator. And I'm going to deliberately make a mistake here and see if you can see what the heck's going on. I'm going to multiply these two together, but I'm going to make a mistake. Negative 3.46 times 4.86, enter. Oops, that's not the mistake, I didn't answer there. Let's do it again from the top. Negative 3.46 times 4.86. The calculator, oh, of course, the calculator won't let me make my mistake. It's deliberately fixing it for me, and it's not fixing it in a nice way. Okay, I'm going to do the entire calculation then with my mistake. So it's going to be 85.7, add a bracket, negative 3.46, close a bracket, times a bracket, 4.86, close the brackets. Well, you look at that, it looks right, doesn't it? Right, 85.7, check. And add a bracket, this guy, a bracket, this guy, bracket. But syntax error. What did I do wrong? About to tell you, but did anybody see what I did wrong? It's so hard to notice on the screen because it looks perfectly right. It looks exactly like that.
Just a guess.
Go
Just
for
a
it.
guess. Do you have to put a bracket around both the negative 3.46 times 4.86.
Oh, you mean
No?
if I took the brackets away or something, it wouldn't matter?
Like a bracket and then bracket negative 3.46.
Oh, some more brackets even. That makes sense.
Let me try it. Let me try.
That's not the reason. I'll show you the reason. Do you notice this little guy down here? Where my finger is pointing, right down at the bottom? In white? Do you know that's a negative symbol?
Oh, that's the negative.
And that is very like a negative symbol, but isn't that the subtraction symbol? And I know in math, we very often mix and match those two words because they kind of mean the same in a kind of very vague way, but strictly speaking, it's not. So I'm now going to do that calculation with the one fix that I need. So it's 85.7, add a bracket, negative 3.46, negative 3.46, close the brackets, times 4.86, close the brackets. And don't you tell me I'm wrong, because I know I'm right. 85.7 plus a bracket, negative 3.46 times 4.86, close brackets. There. So the original score that that person got would be that. You might be expected, say, to round it off to the nearest whole number. So that person probably got 69 on the test. And do you notice that the number that they got was a lot less than the mean? And why was that? Because this is a negative z-score. Okay, so moral of that story, watch out for negatives because you need to hit the negative button. Don't hit a subtraction when you're really meant to hit a negative. So if you get an error, syntax error, it's probably that guy. Okay, let's give you one to try. It's not hard to do. I'll pick a different question. There should be one up the top here. There is. Okay, so in this question, it's basically question 13. The mean is 85.6. The standard deviation is 4.83. And the z-score is 2.85. So your job, find the data, find what that person got in the test. Last few things. So the mean in this class was 85.6. The z-score was 2.85. And the standard deviation was 4.83. And I should be able to do that in one go. 85.6, add 2.85 times 4.83, and the answer I'm looking at is 99.3655. So 99. That person almost got 100% in the test. Are we comfortable about finding the data when you're told mean, standard deviation, and z-score? Tara?
Is